Yes, good morning friends. Today we are in a new place, new venue, and I hope we are continuing with whatever we have studied in the last earlier class. See, in the last earlier class I was discussing about axisymmetric solids, wherein we had started the finite element formulation using constant strain triangular elements. And in that I have already showed you how the four components of stress and strains are related by a special material property matrix C, which is of size 4 by 4. Here you will have sigma x, sigma y, tau xy are replaced by sigma r, sigma theta, and gamma r theta, and tau r theta, and at the same time you will have epsilon theta and sigma theta. These are the two additional components which you come across in the case of stress and strain. After that we have started with how to derive the element stiffness matrix, how to evaluate the things at the centroid of the triangle by considering the radius of the centroid, that is r bar, which is equal to r1 plus r2 plus r3 upon 3, and then we have developed the expression for element stiffness matrix also. Later on, once we have developed the expression for element stiffness matrix, and I have told you about the varieties of the force terms, how to take into account the force terms. In that, I was just mentioning about body force. See, body force, for example, if I consider body force, exactly what is the meaning of body force? See, just one simple example I would like to give. Imagine that there is a flywheel with a hub here, and this is the axis, and this is your r axis, and this is your z axis. And this flywheel is rotating around this with omega radians per second. So as you are already knowing, the actual components of you can say Fx and Fy are the two components of the body forces which are acting in both x and y direction. So in the present case, if you consider the weight, let us say let rho is the mass density in kg per meter cube. If I take this is the rho is the mass density, what we have considered, mass per unit volume, then obviously the centrifugal force, see, it will be considered as a static condition only, with the Fx component being rho omega square r. This is going to be the centrifugal force which is acting in the r direction. Whereas the self weight, which is going to be in the negative direction, I can write it as rho g. Here's you can say this is nothing but our Fy component. So if somebody asks you what is the elemental body force vector, it is rho omega square r minus rho g transpose. This is going to be the, what you can say, the two components of the body forces which are acting on the, it is an example of a rotating flywheel, you can say. This is called a rotating flywheel. See, for the rotating flywheel, you can use this concept and you can find out the body force components. Okay. Yes. Next, we will go for the traction force. Always remember, traction force acts along the edge of the solid. So therefore, let us consider traction. Okay. It's called traction force or surface traction. It is also called as surface traction. Okay, these are the two names which are given. Let us consider one of the edge. For example, before doing this, I will consider one of the edge. Let us say some point we want to take R. This is acted upon by a uniformly distributed pressure. It is, remember, this is going to be uniformly distributed traction or the force of the pressure along the edge. If you consider this as 1 and 2, obviously these are the 2 degrees of freedom, Q1, Q2 and Q3 and Q4. And since we are not coming across the third node, so there is no question of Q5 and Q6, only these are going to come. This is the length of the edge 1, 2 is going to be given by this. And the two components of forces which are acting here are going to be TR and TZ. TR and TZ are going to be the two traction components which are going to be there. See, you can find out R in this case N1 R1 plus N2 R2 only. There is no question of N3 will not come into picture, because this is your, if I say this is my axis, see this radius is your R1 and this radius is R2. So if I know R1 and R2 and Z1 and Z2, with the help of this I can evaluate that. And then L12 can be obtained by R2 minus R1 whole square, Z2 minus Z1 whole square. So this is the way you can use this to find out the length of the element. Okay. Now the real expression for traction force is, we have seen in the last class, it is equal to U transpose T into R into dl. This will be converted into Q transpose into TE. This is the, you can say, for every element this is there. Of course, here your nodal displacement vector consists of only 4 displacements, Q1, Q2, Q3 and Q4 only. There are no Q5 and Q6 are not coming into picture, because since the edge, it is acting only along the edge 1, 2. Node 3 is remaining silent, it is not going to come into picture, so this will not be taken into account. Whereas this T vector is obtained by 2 pi L12 into bracket ATR ATZ BTR BTZ. This is the transpose. What is this A and B? A is given by 2R1 plus R2 upon 6. B will be R1 plus 2R2 upon 6. So if you know the values of R1 and R2 and the coordinates and all that, you can easily find out these things. Of course, here since the edge is slant, so therefore R1 and R2 are different. For example, you come across a cylindrical object. For example, if you have a cylinder subjected to like this, and if you take this as your node element or whatever it is, along this edge, for example, the distribution is taking place along this edge. Let us call this as 1, 2, 3 or something like that. Then this particular thing, whatever is there, it is R3 and R1. They are same. So therefore, when the edge is parallel to axis, R1 is equal to R2, correct? So if I put it here, what happens? 3R1 upon 6. So therefore, A and B both will become 0.5 R1. Okay. So they will take the shape of this. This is most of the case it is going to be the case, because we deal with pressure vessels or cylinders subjected to external pressure or something like that. In such cases, the edges will be straight, and we need to find out the, let's say, radius and the constants A and B need to be evaluated for that. Okay, let us quickly take one simple example on this, which is a very, very common example in most of the examinations. Okay, so let us quickly take one example on that. An axisymmetric body with a linearly distributed load, on the conical surface, on the conical surface is shown in figure. It's shown in figure. Determine the equivalent point loads. Determine the equivalent point loads at nodes 2, 4, 6. Okay, the problem statement gives you, this is our z-axis, this is our r-axis, this is the origin O. The structure is given like this. This is, of course, it is not needed, it is simply a dummy, because what we really need is 6, 4 and 2. This is joined here and this is joined there. This is the plate with the triangular modulation. Yeah, interesting point here is, there is a linearly varying load. It is not constant load throughout this. Okay, we will not consider this extra H. This is only up to this. Okay, we will consider this. Here, we have all these things are acting here now. These are, of course, at the same time they are acting in the downward direction also. And if you look at this, this is 0.25 megapascal, this particular thing. And here it is 0.4 megapascal. Okay. So we need to convert, because what expressions what we have is only for the average, you can say the uniformly distributed traction. So, but whereas it is varying from linearly one pressure to another pressure. So, what we will do, we will find out the average midpoint. The midpoint pressure, if we take P mid 0.4 plus 0.25 upon 2, that is 0.625 upon 2 will be taken as point 325. Okay. Further again you can do the next one is P1 if you want 0.4 plus 0.325 upon 2 will give you 0.4, 0.35 will get here. And similarly, if you take P2, 0.325 plus 0.25 upon 2 will give you 0.25 megapascal. So what I did is, I have converted this particular load, whatever is there, into two uniformly distributed load like this. Up till here it is one load and another load is up till here now. So if I take like this, see these are now going to be the two averaged loads, you can say, like this. We are making an approximation, that is we are converting that into this. This is going to be now 0.35 and this is going to be 0.25. Okay. So these are the two final forces which are acting on this. So now if you look at these edges 2 and 6, if I take this, the 2, 4, 6 if I take, you are already knowing these are the force components which are going to act here. This is F3 and F4, F5, F8, okay, F7, and this is F12 and F11. So these are the 6 forces we need to find out from this particular analysis, and these are going to be added in the global load vector. So first we need to find out the element edge wise. Like first you can consider edge 6, 4 first, then you can consider 4, 2. Of course, the coordinates, if you look at this coordinates, 6, 4 and 2, the coordinates are given, RZ coordinates are given here. It is given as 20 and 70, 20 and 70 for this, 40 and 55 is given for this, and this is for 60 and 40 are given for the node 6. So therefore, with the help of these, we need to find out the required analysis. So let us take first, for edge 6, 4, we will take edge 6, 4. Okay. So let us see what are the details. Pressure is 0.35. Pressure is 0.35. R1, it is 60 mm. Z1, 40 mm. R2, for this, it is 40 mm and Z2 is 55 mm. Okay. We are taking for these two elements, that is these two I am taking, 40 and 60 and 60 and 40, like that. Okay. Now, we need to find out the length of this edge, which is going to be R2 square minus R1 square. Even though, because we are squaring them, there is no problem. Okay. So finally it is going to be squaring. So the length of the edge comes out to be 25 mm. The length of this edge 6, 4 is going to come 25 mm. Now let us consider Z now. C, Z2 minus Z1 upon L12, which is coming 0.6. This is the cos theta component, and S is coming R1 minus R2 upon L12, which is coming 0.8. Therefore, TR comes out to be minus PC, which is minus 0.21. Okay, this is PC. P is 0.35 into 0.6. Similarly, TZ comes out to be minus P into sin theta, which is coming minus 0.28. So once you know these components TR and TZ, we know that A is given by 2R1 plus R2 upon 6. This comes out to be 26.67. That is the constant A. And the B comes out to be 2R1 plus 2R2 upon 6. So this will come 23.33. Okay, this is what you are going to get this. With this, let us now calculate the various forces. That is the traction vector for first edge. 2 pi LE is 25 into bracket ATR. It is ATR, A into TR. If you do that, minus 879.65 minus 1172.9 minus 769.9 comma minus 1026.25. This much. What is all these are the newtons. These are the various forces which are acting on this. Now what you have found out is these four components you have found out. But remember, these are not final ones. Whatever you have found out only belongs to this edge. These you have found out. So these are nothing but F11, F12, F7 and F8. But these two are going to repeat again in the next case, and again we are going to recalculate that. Okay. So now let us go to the next edge. That is 6 to 4 2. Okay. Now let us say for edge 4 2. Now see here. What is the new coordinates for this? Tell me. The new coordinates are pressure is different. Pressure is now 0.25 and R1 is going to be now 40 mm. Whatever the R2 was there for the previous one, that will become now R1 and Z1 for this. Okay. Now similarly for the next point load 2, R2 is going to be 20 mm and Z2 is 70 mm. Okay, these are going to be your new coordinates of the line. Now you can calculate the length 1 2, which is going to be R2 minus R1, 20 minus 40 whole square, 70 minus 55 whole square. So this again will give you same edge, that is 25 mm only. It is going to give you now this. So once you know, you can find out the cos theta. Cos theta, which is we call it as C, which is Z2 minus Z1 upon L12. Z2 is 70 minus 55 upon 25, that is 20. This is coming 0.6 only, 0.8. It comes 0.8. Okay. 70 minus 55. Correct? Huh? Yeah. Then this is coming 0.6, yeah. Yes. And sin theta, S is nothing but R2 minus R1 upon R12. Okay. Say R1 is bigger, so R2 is this. So R1 is 40 minus 20 upon 25, which is coming 0.8. So once again, you calculate TR, which is minus CP, which is going to come TZ minus SP. This comes out to be minus 0.15 minus 0.2, which is going to come. Now once again, we need to calculate this traction at the second element, that is T2. What is that I have given? 2 pi L12 into bracket 2 ATR TZ ATR ATZ BTR PTZ. Now A for this particular edge, 2R1 plus R2 upon 6. That is 2 times 40 plus R2 is 20 upon 6. So A comes out to be 16.67 for the second case. This is what you are going to get. Similarly, you calculate the B part. B, what is B? R1 plus 2R2 upon 6. Okay, so this will come 40 plus 2 into 20 upon 6. 13.33. So therefore, your next this element will come. Yes. Let us put all these values in this equation and then get it. Minus 392.7 minus 523.6 minus 314.16 minus 41.8 88 transpose N. Okay, so this will give you the second components. Now tell me, what are these forces as far as this is concerned? So obviously, if you look at this, these are F7, F8. This is F3 and F4 as far as that is concerned. So therefore, if I want to find out the global, see now here, what is this common? This part and this part, F8, which are repeated here also, because these are the contributions from two different elements, yes, because the pressure distribution on both the edges are different, but node 4 being a common node, the total loads are getting added there. So therefore, if I want to find out the global, you can say equation, which is going to be F3, F4, F7 and F8, and F11 and F12. If I want to write all these things after the clubbing, final answer is minus 314.2 minus 418.9 1162.4 minus 1696.5 879.7 minus 1172.9. These are going to be the final components of all the forces which are going to be acting there like this. So once you know other things are routine. Point loads are taken as in the same routine fashion, even though they are distributed along the ring at several nodes. At a particular specific node, that particular point load will be adding to the given, you can say, load vector, and with that, you will be solving for the famous equation, that is KQ equal to F. Once you solve for KQ equal to F, what you will get is all the nodal displacements you will get. And with the help of nodal displacement, then you can find out the strain components. With the help of strain, then you can go to stress components. So that is generally that is the method which is to be followed here in this case. So we'll take up this. Now we'll just take another one simple example. I'd like to mention you here also. This is also one very interesting thing. This is an example. Here there is a cylinder. He has given a long cylinder which is fitted inside. Okay, this is actually fitted inside a hole. So this edge is going to be literally fixed here. Like this is inserted in a hole, and this is the axis, and this is the thickness of the cylinder. You can say this is the thickness of the cylinder with cross section. So I will hatch this. Then the internal pressure is acting inside this. It is a uniform pressure, like you can see that. You can consider uniform pressure. The pressure is 2 megapascal. The pressure acting on this is there. And here he has given the internal diameter of this. It is 80 diameter, and the diameter of the outer one is 120 mm. This is the outer diameter of the cylinder. And some of the properties which are given are Young's modulus is given 200 megapascal, and the Poisson's ratio is given 0.3. Okay. So we are required to make a finite element model. She has definitely mentioned using two elements on the 10 mm length. You have to use two elements here. If you consider the thickness, at some point you consider this thickness, this is going to be of 10 mm thickness. Okay, and you will have to take two elements here, like this one element and this one element. See, what is the interesting point? Since this edge is completely fixed, only these two nodes can go inside. These are literally fixed from moving outside. So these two, if you look at the boundary conditions, these two nodes are literally fixed because the wall is snugged fit inside a hole. So therefore, no question of expansion of the outer cylinder. Only inner cylinder can expand because of the pressure which is there. So therefore, if I make a FEM model of this figure like this, see here, because this is not going to move, I will fix this. Even this is also not going to move, I will fix this. And the thickness of this element is 10 mm. And since this is going to move, we will keep it on roller support because there is a possibility of deformation. So therefore, this is our 1 and this is our 4. See, when this distributed load, whatever it is along the edge 1 and 2, if it is converted into what you can say equivalent load, these will become F1 and F3 because you know the forces which are acting are in the x direction are F1 and F2. So since there is no F2, there is not considered. Here the forces are F3 and F4. Out of this there is no vertical component, all the forces are there. So there are two forces, F1 and F3, which are acting in the x direction only. Okay, this is going to be the naming. Now you can consider one element at a time and note down the radius of all the three. Of course, whatever you are seeing here, these are the global node numbers. But you can have your own, you can say, element node numbers are given. That is, the local node numbers are going to be given separately. I think probably we will do that. That is 1, 2, 3. 1, 2, 3. We will give it that 1, 2, 4. And for the other one, 2, 3, 4. 2, 3, 4. We will give like this. These are going to be our local node numbers. So for example, now see here, what is this radius? Now tell me, it is a radius. So this is going to be 40 mm. And if you take this is half of 120, that is 60 mm. Okay, we will take, this is the model for this. Now first write the element connectivity. Let us write. The first one is, there are two elements, 1 and 2. And connectivity for the local to global. See, always there are 3 local nodes, 1, 2, 3. And these are given the names. 1, 2, 4 is for the first element. 2, 3, 4 is the second element. You can see here. This is what, this will fix up the values of R1, R2, R3 and all that. That will be fixed up by this. And if you look at the coordinates of this, now let us come on. Let us took the node. These are the coordinates. R and Z. Of course, there are totally 4 nodes. 1, 2, 3, 4 nodes. First one is 40 and 10. 40 and 0. 60 and 0. 60 and 10. See, we are considering this as our initial this thing, and this is our thing. This is R and this is Z. Even though it is Z, but when we talk about the local coordinates, one is, this is quite wide, this one. So this is 40, this is 40. Okay. So that is 40 and 10. What about the second one, node 2? Node 2 it is what? Yeah. Node 2 it is again 40, but since this is the, we are considering this as our R axis, so naturally this is 0, like that. You can find out that. And I have already given you the expression for the material property matrix. Already I have given you in the last previous class how to find out the material property matrix of 4 by 4. So if we substitute these Young's modulus and Poisson's ratio which are given there, So I will directly show you what is that we are going to get this. 2.69 into 10 raised to 5, 1.15 into 10 raised to 5, 0, 1.15 into 10 raised to 5, 1.15 into 10 raised to 5, 2.69 into 10 raised to 5, this is 0, 1.15 into 10 raised to 5. These are 0, 0, 0.77 into 10 raised to 5, and this is 0, 1.15 into 10 raised to 5, 1.15 into 10 raised to 5, 0, 2.69 into 10 raised to 5. Okay, this is going to be a 4 by 4 matrix. So we need it for further calculations and all that. Then these forces which are going to be there, that is F1 and F3, are going to be equal on all this thing. They can be found out by 2 pi R1, length of the element into the pressure, upon R2. This is what you have to get. So obviously 2 pi, inner radius is 40, length of the element is 10, pressure is 2 megapascal divided by 2. So this comes out to be 2514 Newton on both the nodes. The force is going to be equal on both the forces. So therefore, we will consider this as the two forces. Once you know this, now the next important is here for CST element, before calculating the strains or the element stiffness matrix, we need to calculate the B matrix. For each element, we have to calculate the strain displacement matrix. And once you know that strain displacement matrix, then we can calculate the, you can say, K matrix. That is, you can write down the element stiffness matrix for both of them. Then you can make the global assembly of these two, and then you can solve for the nodal displacement with the given boundary conditions. The KQ equal to F will be solved, and what we get is the nodal displacement. What he has asked is to find out the nodal displacement at these points, especially Q1 and Q2. Okay, so we'll take up the remaining part in the next class. We'll do that in the next class.